Good afternoon, everyone. Welcome to today's talk. As many of you have probably know or heard my presentation 2 years ago during Pulse on the Nile, which was dedicated to building dipinti at el-Bahari. This is a kind of continuation of that talk. I thought it might be worth it to present the toolmarks pattern analysis itself as a newly developed approach for technological studies on stone blocks at el-Bahari, its surroundings, and beyond. Toolmarks pattern analysis, morpho-technological studies on ancient Egyptian and Nubian building stone blocks, possibilities and limitations. Sorry, presentation doesn't go. Okay. Introduction. The site of Deir Bahari, known in ancient Egyptian as Gesseret, what can be understood as Sacred Valley, is located on the western bank of the Nile in northern Theban necropolis within a natural bay in the cliffs of modern-day Luxor, Upper Egypt. Archaeological and textual evidence indicates that western Theban necropolis was in use from the Old Kingdom to the Greco-Roman period, serving as a burial ground for both royals and non-royal elite. In late antiquity, it was repurposed and inhabited by Christian Coptic monks. The earliest securely attested structure at el-Bahari is the mortuary temple complex of Mentuhotep II Nebkhepetra, dated to the beginning of the Middle Kingdom. However, the site's most significant development is mainly attributed to the early 18th dynasty, especially under Hatshepsut and Thutmose III, who built their respective temple complexes there. The growing significance of the necropolis coincided with the Thebes' rise as the capital of Egypt and the establishment of a new royal burial ground in the area. Since 1961, the Polish Centre of Mediterranean Archaeology, University of Warsaw, has held the concession for the el-Bahari temples. Excavations began at the Hatshepsut temple proper and then extended to Thutmose III temple proper following its discovery in 1962. The PCMA primary mission was, and still remains, the reconstruction of the key architectural parts of the upper terrace of the Temple of Hatshepsut, alongside continuous excavations, documentation, and study of both temple complexes. Since the Polish expeditions began work at the el-Bahari temples, thousands of limestone and sandstone blocks and their fragments have been returned to their original places, with over 13,000 still awaiting its incorporation into physical or at least theoretical reconstruction. Similarly, more than 5,000 fragments of blocks from the Thutmose III temple proper remain to be attributed. During this work, what is important for the subject under discussion today, many examples of building dipinti that are inscriptions or marks made during the construction process were observed on these thousands of blocks. They were first noted in the Thutmose III temple and later in the Hatshepsut temple. However, this material was not studied in a systematic way until the past 20 years. Between 2006 and 2016, I carried out the first systematic documentation and analysis of the building dipinti at both temples as part of the scientific works of the Polish Egyptian Archaeological and Conservation Expedition to the Temple of Hatshepsut, and then the Polish Egyptian expedition to the Temple of Thutmose III at el-Bahari. In total, 855 dipinti were recorded, where 591 in the Hatshepsut temple and 264 in the Thutmose III temple. Early in this work, it became clear to me that traditional epigraphic methods, which focused solely on the hieratic inscriptions, without considering the archaeological context, were insufficient for full understanding and significance of the dipinti, particularly the temporal and spatial placement. Seeking a method to establish a relative chronology of the dipinti, my inspiration came from Abydos, where limestone flakes with dipinti were found in the stonemasons' production dump, who worked on the construction of the mortuary temple of Senuseret III, the king from the 12th dynasty Middle Kingdom. There, among thousands of limestone flakes, numerous examples were found in fragmentary preserved building dipinti, clearly damaged during the dressing process of large limestone blocks when the flakes were detached. This led me to hypothesis that understanding the stone blocks production process could help me to determine when the dipinti were executed and better contextualize them. So I got to work. In order to carry out the technological analysis of the building stone blocks in the temples of Hatshepsut and Thutmose III at el-Bahari, I decided to apply the so-called scare pattern analysis method, originally developed for studying assemblages of Paleolithic flint tools. For the purposes of my research, however, the method was significantly modified to accommodate additional data not present in flint material. I named this adapted approach Toolmark's pattern analysis method. The Toolmark's pattern analysis method is a complex, multi-phased approach, and its analytical procedure consists of several stages, which are selection of diagnostic material, defining of stone material orientation, identification of evidence, defining of evidence variables, such as orientation of the tool drive direction and mortar flow direction, sequencing of evidence, and spatial distribution of evidence. Then evidence analysis, sequencing of stratigraphic units, and reconstruction of the technological production process. Selection of diagnostic material. Toolmark's pattern analysis, abbreviated as TMPA, is a method that requires direct work with the original stone material. Thus, all analytical and descriptive procedures should be conducted on site as they were in the case of the el-Bahari material. The analysis focused on blocks bearing building dipinti primarily from freestanding and retaining walls, as well as structural infills of artificial platforms. The technological analysis included well-preserved representative groups of diagnostic blocks, allowing to collect detailed data. The best result in the TMPA method can only be achieved by analyzing all 6 faces of each stone block. Therefore, the primary material consisted of well-preserved, movable, loose blocks. Supplementary data were obtained from blocks still in situ within the temple of Hatshepsut, limited to the accessible front face only, and from several ton infill blocks of the artificial platform of the temple of Thutmose III, which could not be moved or rotated. A principal criterion for selection is the presence of distinct, well-preserved tool marks that are sufficiently legible to reveal not only the types of tool used, but also distinct phases of the dressing process. Heavily eroded or post-depositionally damaged blocks are systematically excluded in the method. Ultimately, in the case of the el-Bahari material, 23 representative blocks were selected from the temple of Hatshepsut out of 573 inventoried, and 8 from the temple of Thutmose III out of 181 inventoried. These examples formed the basis for the illustrating the application of the TMPA method in the reconstruction of the building stone blocks dressing technology employed during the construction process of both temples in the early 18th dynasty of the New Kingdom. Defining of stone material orientation. A profound significance for the TMPA method is its ability to present a stone block in an unfolded six-faced view. Therefore, accurate identification of the stone block's original orientation is essential, as it enables a correct technological analysis of the material in later stages of the adopted analytical procedure. For the purposes of the TMPA method, the descriptive model is based on a standard wall block whose 6 faces provide a framework. The keep things consistent, the same descriptive system is used for all stone blocks even if their original orientation is unclear, as was the case, for example, with the el-Bahari infill blocks, for which determining the original orientation is often difficult or impossible. Each block is divided into 6 phases, starting with the front face and described in a fixed order based on the chosen naming system. Phase A, the front face of a block, which forms the outer face of a wall structure. Phases B and D, the right and left side faces of a block, which form within a wall structure the right and left rising joints between it and other blocks in the same course. Phase C, the block side face, the back side face of a block, which forms inside the wall structure the rear face of its front face. Base C, the base side face of a block, which forms its lower bed, and inside the wall structure, the lower horizontal joint between it and another block or blocks of the lower course. And phase T, the top side face of a block, which forms its upper bed, and inside the wall structure, the upper horizontal joint between it and another block or blocks of the upper course. Identification of evidence. The initial analysis of the stone building of the stone blocks aimed to identify the main categories of evidence observable on all 6 faces of a stone block. At the el-Bahari, 3 primary categories were recorded: tool marks, surface deposits, and various types of post-depositional damages. The most abundant category consists of tool marks, predominantly negatives, resulting from using different types of tools. These negatives form part of a large concave surface known as flake scarce, created by the detachment of flakes from the core of a stone block surface. The terminology used to describe the flake scarce is again adopted from lithic studies, that is flint tools analysis, with modifications made to fit the context of building blocks. Within each flake scare, the strike point and accompanying gutter representing the negative or imprint of the working blade of used tool are typically visible. At the el-Bahari, these tools' negatives range from 10 to 40 mm in width. As for the flake scares, 8 distinct types were identified based on their shape and size, such as shelly, linear, flat, curved, split, thick scratched, and thin scratched. Additionally, technological evidence includes construction-related deposits such as mortar, as well as the features not directly related to the technological production process of the stone blocks. These include relief decoration, recarvings, and various forms of post-depositional damages, whether anthropogenic or natural, none of which are relevant to the technological focus of this analysis. Defining of evidence variables. An important stage in the technological analysis of stone material is the identification and recording of observable evidence variables, which are essential for interpretation of the tool marks and reconstruction of the technological production process of building stone blocks. These are orientation of tool drive direction and mortar flow direction, sequencing of evidence, and spatial distribution of evidence. Orientation of tool drive direction and mortar flow direction. The tool drive direction, abbreviated as TDD, refers to the direction from which the deliberate action, such as strike with a tool, was applied to shape the stone surface. In the case of flake scars, this direction is determined by interpretation of this strike point, ripple marks, radial lines, and interscarce ridges observed on the scar surface. Similarly, the mortar flow direction, abbreviated as MFD, is identified based on the observable flow direction of the applied material. Both TDD and MFD are described in accordance with the adopted procedure, which is based on an 8-degree scale, counting clockwise direction from 1 to 8. Referring to sequencing of evidence, this step involves organizing tool marks and mortar traces into sequential groups. These sequences are defined by shared metric variables, suggesting that the tool marks within a sequence result from a single intentional technological action in the dressing process carried out with a specific tool on a specific part of the stone block. As for spatial distribution of evidence, the spatial distribution of evidence results directly from the sequencing. At el-Bahari, this made it possible to distinguish surface dressing zones across the 6 faces of the model stone block, what can be presented in the form of a diagram. These zones, defined both horizontally and vertically, represent distinct areas, zones, characterized by specific dressing techniques, as determined by the sequencing of tool marks and deposits. Each zone is associated with particular types of tool marks and presence or absence of deposits, recorded exclusively within its boundaries. In the el-Bahari material, the stone blocks surfaces were divided into 9 surface dressing zones, numbered from the back face to the front face. Evidence analysis. Based on the identified repertoire of categories and types of tool marks, it is possible to distinguish tool mark sets, abbreviated as TMS, which occur on specific faces of building blocks within defined surface dressing zones, as estimated for the el-Bahari material. Not all tool marks are present on every face. Sequential analysis of flake scars indicates that identical tool marks types may appear on multiple faces or even within a same zone of a single face. However, they can be evidence of different technological actions. Importantly, different tools can produce similar flake squares when used for the same technological purpose. This is further supported by the discussed above tool drive direction characteristic for each tool mark set. Accordingly, individual tool marks inventories can be compiled for each face of a model stone block as it was prepared for the el-Bahari material. 63 tool marks were identified for the front face, 31 for side faces, 16 for block face, back face, 21 for base face, and 28 for top face. However, this diversity does not imply the use of an equivalent number of tools. Comparative analysis reveals that direct tool marks types are components of specific TMS employed to perform specific technological actions. Thus, in the example of the el-Bahari material, the initial counts for tool marks can be consolidated into the tool mark sets per face as follows. Front face 26 TMS, side faces 14, back face 8, base face 10, top face 15. Sequencing of stratigraphic units. A key stage in the toolmarks pattern analysis method, central to reconstructing the technological production process of building stone blocks, is the identification of stratigraphic relations between individual toolmark sets, enabling the establishment of the relative chronological sequence. Similarly to the scale pattern analysis of flake squares in RITIC studies, stratigraphic units are defined by estimating the extent of the TMS and interpreting the superpositional relations on block faces and edges. This allows the establishment of the chronological order of tool marks and deposits, not only within a single face, but also between faces. Thus, the sequencing procedure consists of 3 stages. 1. Stratigraphic relations are first established separately for each phase, identifying the number and sequencing identifying the number and sequence of stratigraphic units per phase. Second, these are then integrated to determine stratigraphic relations across all 6 phases. 3. Finally, these stratigraphic relations are represented using modified Harris diagrams, as has been done for the el-Bahari material, where each TMS is treated as a stratigraphic unit, shown as a rectangle labeled with TMS number. Lines between units indicate superpositional relations, while the vertical arrangement reflects chronological order according to the law of superposition. The sequencing procedure reveals the main stratigraphic units are usually shared between multiple phases, sometimes all 6, indicating a single unified technological action. This is represented in the Harris diagrams by double horizontal lines connecting identical units across phases at the same level. Additionally, recurring sequences of tool marks types can be observed, allowing identification of specific points in the technological process where a particular tool type was introduced for the first time. Ultimately, sequencing enables the reconstruction of a complete chronological sequence of stratigraphic units, as demonstrated in the case of the el-Bahari material, where 41 stratigraphic units were distinguished. Each stratigraphic unit is defined by a characteristic tool mark sets a tool drive direction and is associated with a surface dressing zone on a given face. Reconstruction of the technological production process. The final stage of the toolmarks pattern analysis involves the reconstruction of the complete technological production process of building stone blocks. To structure this reconstruction, the concept of chain opératoire, the sequential chain of operations, was adopted. This reconstruction is based on the stratigraphic sequence of identified stratigraphic units, each representing a distinct pre-planned technological action necessary for producing a building stone block. Within this framework, the chain opératoire is temporarily structured by the stratigraphic relations between stratigraphic units spanning from raw material acquisition quarrying to post-depositional processes, as illustrated by the example of the el-Bahari material. To refine the complete the proposed reconstruction, it is necessary to re-examine the recorded tool marks types and identify the specific tool sets used by ancient stone masons in dressing stone blocks, as observed in the el-Bahari case study. They identified tools were metal bar chisels used with wooden mallets, supplemented by saws, grinders, and mortars. These tools functioned primarily as cutting implements for both stone extraction and subsequent dressing. Depending on the tool type, the applied force, and the required precision, stone flakes were detached in a manner analogous to flint tools, using various core reduction techniques to produce a final product, in this case, a building element. Analysis of tool marks allows for the interpretation of tool functions and by extension to indicate distinct phases in the technological production process. Chisel function appears closely related to the blade width. Narrower chisels penetrate deeper, producing larger flake scars, while wider blades yield smaller, shallower scars. This indicates a workshop practice of progressing from narrow to wide chisels during dressing. In the el-Bahari material, chisels ranged from 10 to 40 millimeters in blade width. The most illustrative example is the front face, as it is exemplified by the el-Bahari material, where a standardized 7-stage surface dressing process can be observed, seen from perspective of a single face. Here, all identified operation stages are listed in chronological order. Each operation stage represents a technological operation defined as a distinct dressing action performed on a single face using a specific tool or tool set, characterized by unique negative and flake scar types. In contrast, sets of technological operations refer to coordinated actions across multiple phases performed using consistent tool sets with similar negatives but variable flake scar types. Exceptions occur in stage 5 and 6, where only 2 negative types and mortar are involved. In summary, the el-Bahari stone dressing process can be reconstructed as 7-stage surface dressing process comprising 5 main technological phases, followed by phase 6, post-depositional process. To reconstruct the complete technological production process of building stone blocks, toolmarks pattern analysis focus on the full assemblage of data from an integrated perspective, that is, by considering all 6 phases of the stone blocks simultaneously. As mentioned earlier, the concept of chaîne opératoire was employed to structure the reconstruction, referring to the ordered sequence of operations required to shape and obtain a desired building stone block. This framework is grounded in the chronological arrangement of stratigraphic units, each representing a clearly defined and pre-planned technological action. According to the developed analytical procedure, the reconstruction surface dressing process is reanalyzed both spatially and temporally, covering the entire time frame from raw stone material acquisition, quarrying, to post-depositional processes. This approach facilitates the identification of organized technological actions, which are then grouped into production stages and broader technological phases. In the case of the el-Bahari material, the chaîne opératoire of the technological production process of building stone blocks can be defined as follows: 25 organized technological actions ordered in a chronological sequence aimed at producing a building stone block. These actions are grouped into 9 production stages, each corresponding to a specific sequence of operations carried out on individual stone blocks faces. All stages are further integrated into 5 technological phases, representing the major components of overall production process, which are Phase 1, acquisition and preparation of the raw material. Phase 2, formation of the stone block. Phase 3, formation of the top face of the stone block. Phase 4, final dressing of the front face. Phase 5, relief decoration, and phase 6, secondary post-depositional damages. In addition to reconstructing the chaîne opératoire, Toolmark's pattern analysis also considers the transportation of stone blocks as an integral part of the overall production process. Although the stone blocks were undoubtedly repositioned multiple times, their orientation at each stage can be inferred through spatial and directional analysis of the recorded tool marks, which reflect the sequence of technological actions. For the el-Bahari material, this analysis revealed 2 main dressing steps within the technological production process: the early dressing step and the late dressing step. During the early dressing step, which spanned from the raw material acquisition to setting, the stone block was repeatedly rotated to allow full access to all 6 faces. In contrast, during the late dressing step, which spanned from trimming the top face to the execution of relief decoration, the stone block was immobilized with only the front and top faces remaining accessible. As a result, 5 transportation phases and 5 corresponding workshops, each with their own subdivision, were identified. These reflect changes in the position, location, and accessibility of stone block throughout the production and transportation phases. To summarize the results of the research on the stone and epigraphic material at the el-Bahari, as mentioned at the beginning of my presentation, the Toolmark's pattern analysis method was originally developed for epigraphic purposes at the el-Bahari, specifically to stratify building dipinti in the temples of Hatshepsut and Thutmose III. When applied in accordance with its original purpose, the method yielded consistent results: stratigraphic relations between the dipinti and tool marks with deposits sequences enabled their integration into the reconstructed chaîne opératoire. As a result, 7 stratigraphic horizons were identified, within which the recorded building dipinti were inscribed during the technological production process of the building stone blocks. Application of the toolmarks pattern analysis on the other sides. The original goal of developing the toolmarks pattern analysis method was to create a system for stratifying epigraphic material. However, it quickly became clear that this also provided a way to identify and describe the morpho-technological features of building stone blocks, features directly shaped by their characteristic production processes typical for certain groups of stone blocks. This led me to an idea: if the morpho-technological features of stone blocks from a safely dated archaeological context can be precisely described, then similar stone blocks from unknown contexts may potentially be dated by comparison. After completing my research at el-Bahari, I applied the TMPA method on material from other sites, Marea, Philoxenite, and Berenike in Egypt, and Old Dongola in Sudan. Comparative analysis revealed that well-documented material from the 18th dynasty helped to recognize similarities in stone dressing technologies in much later periods. This observation supported the hypothesis of a long-term development lineage in soft stone dressing technologies, extending from antiquity into post-antique period. However, application of the TMPA outside el-Bahari showed also some limitations. The exceptional conditions at el-Bahari, like the large amount of well-preserved and relatively homogeneous material, are rarely found at other sites, especially at settlement sites. For the TMPA method to be fully effective in reconstructing the technological production process of a given assemblages of building stone blocks, three principal conditions must be met. The analyzed material should initially form a homogeneous set originating from a single architectural structure or part of it built within a defined time period. A sufficient large sample, preferably several dozen well-preserved loose stone blocks, must be collected, and the sample should represent the full range of production stages from the initial to the final dressing to enable the complete reconstruction of the process. As it turns out, however, outside el-Bahari, maintaining the principal analytical conditions required for the full application of the TMPA method is exceptionally difficult. In the most cases, the stone material is heavily mixed and poorly preserved, primarily due to natural conditions, which significantly complicates the analytical procedure. In order to overcome this problem, I began using a shortened version of TMPA procedure focused on a partial reconstruction of the technological production process, specifically the surface dressing process, carried out as if from the perspective of a single phase, illustrating in chronological order the identified technological operations as was done at el-Bahari in a standard procedure. Also, this shortened approach limits the analysis to a single phase of a stone block. It still provides a meaningful and consistent results. It allows for the documentation of key evidence categories associated with the technological actions, namely types of negatives, flake scarce, and deposits, and enables to stratify the entire process into technological operation stages and then technological phases. As a result, even under restricted conditions, it is possible to describe the characteristic morpho-technological features of a given assemblage of stone blocks, allowing comparative analysis and potential chronological assessment. To facilitate comparative analysis of dressing stone blocks from different provenances and dates, the hierarchical model of archaeological assemblages developed by David Clark proves highly applicable. The idea behind this model is a polythetic classification system based on common diagnostic features, which, like in the analysis of flint tool assemblages, enables the identification of taxonomic units and the assessment of taxonomic distances between them. Applied to the stone material, the model allows for the defining of technological industries, that is, individual taxonomic units with distinct morpho-technological features, technological technocomplexes, that is, clusters of coexisting industries sharing common features, and technological industry cycles, that is, chronological succession of related industries. Thus, based on the classification criteria outlined above, the analysis of the stone material examined at el-Bahari, Marea Philoxenite, Berenike, and Old Dongola has allowed for the identification of 9 distinct technological industries, including Hatshepsut industry, Thutmose III industry, Tutankhamun industry, Ptolemaic industry, Meroitic industry, Tiberian industry, Blemian industry, Marea Philoxenite industry, and Old Dongola industry. Based on the analysis of taxonomic features and distances, the Hatshepsut, Thutmose III, and Tutankhamun industries may be grouped into a single technocomplex, here general named New Kingdom Technocomplex, while the Ptolemaic and Meroitic industries form the Ptolemaic Technocomplex. The Tiberian industry naturally represents the early Roman Technocomplex. The Blemian and Marea Philoxenite industries form the Byzantine Egypt Technocomplex. The Old Dongola industry, although potentially seems technologically aligned with the Roman tradition, so far appears to me to constitute a distinct Makurian Nubia technocomplex. According to the adapted classification, technocomplexes can be grouped into larger units. Hence, 3 distinct technological industry cycles can currently be proposed. 1, Pharaonic industry cycle, including the New Kingdom and Ptolemaic technocomplexes. 2, Roman industry cycle, represented by the early Roman technocomplex. And 3, Byzantine industry cycle, evidenced by the Byzantine Egypt and Makurian Nubia technocomplexes. Among the taxonomic features that define the technological and chronological classification, the most significant are tool sets, dressing techniques, and dressing process structure. Notably, within the Ptolemaic pharaonic industry cycle, as we could see, the 2 principal technocomplex groups can be distinguished, New Kingdom and Ptolemaic. The central feature they share is already mentioned above, the 2-step dressing process, in which stone blocks were dressed in 2 steps, before and after setting, serving as a main criterion for grouping them within a single cycle. In contrast, both the Roman and Byzantine industry cycles represent the 1-step dressing process in which stone blocks were fully dressed prior to setting, functioning as full dressed architectural element. In terms of further basic common features, clear distinctions can be observed among the identified technocomplexes. Within the New Kingdom technocomplex, a standardized chisel set with blade widths ranging from 10 to 40 mm was employed, complemented by the use of saws for joining planing. A characteristic morpho-technological feature of the stone blocks is the presence of proto-anatherosis that is carefully flattened and planed joint edges. In the Ptolemaic technocomplex, the toolset evolves with the introduction of finer chisels with cutting blades measuring just 5 mm in width, while classic Greek anatherosis replaces the earlier proto-anatherosis. Notably, the same set of diagnostic features is also observed in the Meroitic industry, suggesting technological tradition continuity. In contrast, the early Roman, Makurian Nubia, and Byzantine Egypt technocomplexes show significant changes. The Roman industry cycle, with its technocomplexes, introduces extremely narrow chisels with cutting blades measuring between 3 to 5 mm in width, alongside toothed tools, either chisels or the shahuta adze. The use of anatherosis persists. Technological differentiation becomes even more noticeable within the Byzantine industry cycle. The Byzantine Egypt technocomplex is characterized by a limited tool set dominated by wide blade chisels with cutting blades measuring from 30 to 50 mm in width. Conversely, the Makurian Nubia technocomplex preserves a more diverse chisel tool set with cutting blades ranging from 5 to 20 mm and from 30 to 40 mm in width, while anatherosis remains a consistent feature. In summary, the application of the Toolmark's pattern analysis method to stone material from various sites, when combined with the theoretical framework of polythetic classification, has produced unexpectedly promising results. Despite the limited scope of current research, the comparative analysis of morpho-technological features has revealed a discernible development lineage in the building stone dressing technology across ancient Egypt and Nubia. It has proven possible not only to distinguish diagnostic morpho-technological features characteristic of specific taxonomic units, technological industries, but also to classify them into broader entities such as technocomplexes and technological industry cycles. Also, the outlined general evolution and development lineage of building stone blocks dressing technology in ancient Egypt and Nubia is far from complete and fully understood. It must still be treated as a primary model. Several broader patterns can already be observed. Among the three identified technological industry cycles, the pharaonic industry cycle appears the most technologically complex, featuring the most toolset diversity and the most elaborate operation stages. In contrast, the Roman industry cycle shows a visible reduced and altered tool set and a significantly simplified operation stages. The Byzantine industry cycle presents a more complex picture. The Byzantine Egypt technocomplex is marked by an extreme reduction in toolset diversity, often limited to just one or two types, suggesting a minimalistic approach to stone dressing technology. Conversely, the Makurian Nubia technocomplex displays a richer technological repertoire, both in terms of tool set diversity and a more complex sequence of operation stages, being more closely morpho-technologically aligned with Roman industry cycle tradition. Overall, these facts suggest a gradual simplification of stone dressing technology over time, with a notable decline in technological complexity and craftsmanship by the Byzantine period, particularly in Egypt. With regard to the taxonomic units discussed here, it is important to emphasize that this theoretical framework of technological and chronological classification remains highly, if not extremely, fragmentary and requires substantial further research. To grasp the scale of the necessary investigation, we must consider that I don't yet have documented evidence from periods prior to the Thutmosite era. Further, there are significant gaps in the material recorded from the Thutmosite era through the reign of Tutankhamun and into the Ptolemaic period. Similarly, so far I have found only limited evidence dating to the early Roman period, followed by another gap extending to late antiquity. We can now only speculate on the number and diversity of technocomplexes and associated industries that may have existed during these poorly documented time periods. At present, my focus is on deepening our understanding of materials from the early Middle Kingdom, specifically the late 3rd millennium BCE, as well as in the 1st millennium BCE. The former may shed light on the origins of the New Kingdom technocomplex and the development lineage of soft stone dressing technology within the earlier phases of the pharaonic technological industry cycle. The latter may help clarify the dynamics of technological evolution between the New Kingdom and the Ptolemaic technocomplexes. Conclusions. In conclusion of my presentation, I would like to offer a brief synthesis of my key observations regarding the application of the tool marks pattern analysis method to morpho-technological studies on ancient Egyptian and Nubian building stone blocks. As shown in this presentation, the TMPA method offers a clear and structured procedure for systematically collecting and organizing variable morpho-technological features, allowing for the full reconstruction of the stone blocks production process. Importantly, the TMPA method also offers a degree of methodological flexibility in cases where ideal research conditions cannot be met. The method may be effectively adapted into a shortened analytical procedure, which, while limited in scope, still yields reliable and diagnostically valuable results. From a broader perspective, the TMP method offers significant potential for comparative studies of stone blocks assemblages when combined with the polythetic classification. As a result, in course of further research, it should help to create a morpho-technological typology of the building stone blocks and to arrange it in chronological order, making the TMPA method an invaluable tool for relative dating. Thus, the toolmarks pattern analysis method, originally developed for the relative dating of epigraphic material, has, as shown, evolved into a separate tool for the relative dating of stone building material itself, and potentially it may even provide a basis for the distinct academic discipline to emerge, opening up new possibilities for research in previously unexplored area. Thank you for your attention.